Simple harmonic motion summary. Let's start with Hooke's law. For an object to be in simple harmonic motion, the force has to be linearly dependent on the displacement. And here is Hooke's law. If it is proportional to the square or any other power of the displacement, then the object is not in simple harmonic motion. The force is not constant, which means the acceleration won't be constant either. Right? The force depends on the displacement. So, since the acceleration is not constant, we cannot use the kinematics equations to solve for the acceleration, velocity, or position of the object. A pretty standard experiment with springs and masses is to find the spring constant K. What you do is you have a spring here on the left side, you just have it hanging from a roof or something, or a lab stand, and then you put a mass on it, and you notice that obviously it stretches the spring out. We're going to call the final position here y equals 0 and the initial y0. We draw a free body diagram when the mass is down here. You have ky0 in the up direction because the force opposed the motion. It's always trying to restore it to where it was. And you have mg pulling it down. You sum the forces using Newton's second law. ky0 minus mg equals may, and it's not moving at the bottom anymore. You let it come to rest. So the spring constant is simply found by mg divided by how far the spring was stretched. On occasion, we may want to put two springs in parallel to see what happens. It turns out we want to replace these two springs with one spring and find its effective spring constant, so that one spring will act like the two in parallel. When we do the math, we'll find out that is analogous to putting resistors in series. Maybe you remember that from an earlier physics course. If not, we'll see it again when we do electricity and magnetism in APC. The effective spring constant will be the sum of each spring constant. So here's our derivation. We're going to say we put a mass here, and the springs extend by y. So we have two forces in the up direction, ky plus ky, minus mg is equal to 0 because we're at rest. So we have 2ky is equal to mg. Let's replace that 2k with k effective. So we find that k effective is 2k. And unlike resistors, though, the individual spring constants need to be the same, because if they're not, here's our mass. This will have a higher spring constant. It'll be stronger. This will be weaker, so it'll stretch more. So this thing will rotate, and it won't quite give us the right answer. So when we put springs in parallel, we need them to have the same spring constant, and we just add the two to find the effective spring constant. Now let's put two springs in series, and we want to find the effective spring constant there, where we replace both of those springs just with one. Now what's going to happen here is 1 over k effective is equal to 1 over k1 plus k2. And that's because our total distance here is going to equal both distances that are stretched. So you can go ahead and go back to the simple harmonic presentation and see exactly how we did the math. Here we're just presenting the results. So k effective will be less than either one of the spring constants that were joined together. So the combination will be less stiff than either spring alone with the mass. And you can actually do this with multiple springs, and they can all have different spring constants, unlike when you have them in parallel. And what is this? This is going to be analogous to resistors in parallel. We're now going to calculate the elastic potential energy of a spring. Again, in earlier physics courses, you were probably just told that it's equal to 1/2 kx squared. Now we're going to show you where that came from. So we have Hooke's law, and this is for an ideal spring. It's equal to minus kx. And we want to find the work that the spring does as you have a spring being stretched by an external force. We're going to take it from x0 to x. Here's our force, and it's an integral from force dot dx. And in this case, we'll make x0, 0, and our final position just x. So we put the force in there, which is minus kx, and we do the integration. And we'll come up with the work that the spring does when it's being stretched is minus 1/2 kx squared. To find the potential energy, you take the negative of the work, And there you go. There's 1/2 kx squared, what you learned in earlier physics courses. This elastic potential energy is only relevant for a perfect massless spring that obeys Hooke's law. You're going to be asked at some point to find a potential energy for springs whose restoring force is not dependent on linear displacement. For example, F equals minus kx squared. And what do we mean by the subscript again? We're using the restoring force of the spring to calculate the work and then the potential energy. If a problem gives you the external force, for example, if you're pulling on the spring with a certain force, you need to take the negative of that force to find the spring restoring force and then the potential energy. So be careful with the signs. After a spring is compressed or stretched and released, the total energy is conserved. There are no external forces then, and the energy is traded between potential energy and kinetic energy. So here's conservation of energy, and here are the two types of energy that we're dealing with a spring. We have the potential energy, kx squared, and the kinetic energy of the spring's motion, 1/2 mv squared. And you can see the subscripts. We got the initial position and then the final position. The total energy of the system is given by how much the block is displaced. So it's your maximum displacement, and that's going to be A or negative A, depending on whether you extend it or compress it. You have no kinetic energy at the endpoints, right? It's all potential energy. So your total energy will be your potential energy maximum, which will be 1/2 Ka squared. You can also express the total energy as a function of the maximum kinetic energy. Where do you have maximum kinetic energy? That's where your potential energy is 0. That's right in the middle at the equilibrium point. So your total energy there will be 1/2 mv squared max, where the velocity is your maximum velocity. So we have this extended equation here. Your total energy is 1/2 Ka squared, or when you let it go, you can measure the velocity at the equilibrium point where there's no potential energy, and your maximum energy then is all kinetic, and it's 1/2 mv max squared. Very handy for problem solving. Here's a summary of various periods of simple harmonic motion. Mass spring system, your simple pendulum, then your physical pendulum. This is when you just don't have a simple massless rod with a mass at the end of it. You have some kind of shape or structure. And this C here, that's going to depend on the moment of inertia of whatever object is making up your physical pendulum. Then you have your torsional pendulum. That's where you have a disc, for example, and it's hanging from a rafter or a beam or something, and you just spin this around. Now that actually behaves very similarly to the mass spring system. The force in each case depends on the displacement. In the torsional pendulum, it's angular displacement, and in the mass spring system, it's linear displacement. So you can view the torsional pendulum as the rotational equivalent of a mass spring system, oscillating back and forth. The relationship between the circular motion and simple harmonic motion is best shown in the sinusoidal nature of your simple harmonic motion. We have a plot here of the position versus the time of something in simple harmonic motion, and we're going to say this is the solution to the equation. X of t, the position at any time, is equal to A, which is your amplitude of the system, times cosine omega t plus phi. Phi is just the phase angle. It tells you where you're starting your problem. And then you can take derivatives to find the velocity and then the acceleration. And omega is 2 pi over the period, which is also equal to the square root of k over m. And the way you find omega is you measure the period t on the graph, right? So you could find the period goes from here to here. In this case, the period would be 5. Or you could also find omega if they give you k or m, or k and m. And of course, that works both ways. You find the period, you can now find k over m.